Good afternoon. It's like we have lots of visitors today. Oh, they're leaving. Oh, well. See you guys. Take care.
Sorry, Mr. Strong.
Hey, that's all right. I was wondering if anybody was showing up today.
We have AZ Merit. We had AZ Merit testing today, and so the schedule was all messed up, and I didn't even realize it was 2:50. So I had to run in here, but
Well, I'm wondering if that's the same thing that's going on with Jada. So, whoa. Let's see here. Well, we're going to give her a few more minutes before we decide what to do. But in the meantime, do you have any questions over anything that I could help you with, or?
I don't think so right now. I
Okay.
was working on chapter 9.2, so.
Okay. 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 Oh, there's Jada. Okay. All right. So I was a little worried about you. So is your schedule messed up with AZ Merit as well?
No, it's like on Tuesdays and Thursdays they have this like enrichment thing for math and reading in the morning.
Yeah.
And so like I have to get out of my 7th hour early, and I forgot about today.
Okay. All right. Well, that's okay. I'm just glad you're here. I was a little worried because when it came time for class to start, nobody was here, so I was getting a little nervous. But we're good to go. So basically so chapter 10 is where we're going to start here today. And see, chapter 10 has a lot of sections in it. There's 10 sections. So that's kind of the bad news. But the good news is that most of the sections are very short. The only one that's really of any length at all that I can remember from last year is the first one. And so the first one is the only one that will take probably more than a day for us to do. Some of the sections will actually combine and have like 2 sections in one day. That's how short that they are. And so, but I get a little nervous when I start looking at that I think I have something like 16 more class periods with you guys, and we have 16 sections. And so it makes me a little nervous, even though I know we're okay. Our timing is just going to be okay. But I think if I've done, I think I have, I'm not sure about, I know I have 16 days, but then I'm not sure after that, the last week. So I've got to figure all that out. So anyway, I did go and update the curve on the midterm was 5 points. And so I upped your grade on the midterm, the overall. If there's any other, so go and look at your grades. If there's anything else that we can do, but it looked to me like the biggest thing is you guys just need to take quizzes and tests. So, all right. So, any questions or concerns before we get started on chapter 10? Okay. Now, another thing I'm hopeful about with chapter 10 is that students tend to do very well in this chapter. As a matter of fact, you're going to see that as we go through this first section, even though kind of the explanation might be a little long, to do the actual problems, I think you're going to find that at the very hardest, most of the problems, you have a 50-50 chance. And because the topic, infinite sequences and series, see, you studied those in Math 189 in Trig. And then we're going to talk about whether they converge or diverge. And so a lot of the questions, you had a 50-50 shot at it. But we're going to do better than that. I'm going to teach you how to do it. But before we really jump into 10.1, I kind of want to give you a feel for the idea of an infinite series. Because I know when I was a first calculus student, the idea that you could add up an infinite number of things and get a specific number just sort of blew me away. Okay? Because I thought, well, if you're adding up an infinite number of things, no matter how small, you should get infinity every time. But you don't. So let me try to convince you why that is. So the first few examples I have are kind of visual ones. So the idea is, so imagine you have a trapezoid here that has an area of 1. And you're going to divide that trapezoid into 4 regions. Yellow, red, blue, and green. All right? Then we're going to take this green region and break it into 4 regions. And so one of those regions, we're going to color it yellow. And then we take the green region again and break it down to 4 regions. And so one of those regions, we're going to color yellow. And we could keep going and doing that forever. And so eventually all of these regions here would be colored yellow. So the idea is we have a fourth plus a fourth of a fourth plus a fourth of a fourth of a fourth, or a fourth squared, plus a fourth of a fourth of a fourth to infinity. And the yellow region here it comprises 1/3 of the whole thing. And so to add up all the yellow regions, we would get an area of 1/3. So we have the sum of all these infinite things that add up to 1/3. Now, this is kind of an interesting deal. I've actually seen this in this picture in an art gallery, which I think is kind of fascinating, how an artist could incorporate math in their painting. But this really does, it's the same idea. that you take the area of this square and cut it up into fourths. And so then the upper right corner, we cut it up into fourths and color it gray, black, and white. And then the fourth, we break it up into fourths and color it gray, black, and white. And then break it up, and then you keep going and keep it going. And so then what you have is the same thing, a fourth plus a fourth of a fourth plus a fourth of a fourth of a fourth. And each color then comprises of 1/3 of the total area. So the black, the white, and the gray each are 1/3 of the entire area. Okay? And so different artists kind of have used the same, or the same art. I think this was the same artist that did the same thing, only with a triangle, breaking a triangle down into 4 areas. So we had a trapezoid, a square, triangle, but again, a fourth of a fourth of a fourth, it ends up being 1/3 each time. All right, and then there's the joke that I tell in trig, you might remember it, about how an infinite number of mathematicians walk into a bar, and the first one says, I'll have a beer, and the second one says, I'll have half of what he had, and so that'd be a half a beer, and the second one says, I'll have half of what he had, so that would be a fourth of a beer, and then so on and so on. And so the bartender, knowing math himself, because if you're the bartender in a math bar, he pours 2 beers. And so you might think, well, wait a minute, there's an infinite number of mathematicians. How can it just add up to be 2 beers? Well, in trig, we learned this formula, that a sum of an infinite geometric series is S over A sub 1 over 1 minus R, where S is the sum, A sub 1 is the first term, and R is what you multiply each time. And so here we would get S equals 1 over 1 minus a half, because each one is a half. So 1 divided by a half is the same as 1 times 2, so 2. So the bartender was correct. Now, there's actually another part of that joke, but it actually requires Calc 3. So if you do take Calc 3, you'll have to remind me to tell you the next part of the joke, the Calc 3 version of the joke. My son sent it to me, and it's actually pretty funny. But anyway, so we get the sum of an infinite number of things being a finite number. So you have an infinite sequence. Well, in this case, where you have an infinite arithmetic sequence, and we do the sum, we use this little sigma. Okay, this is the sigma notation. And here, if we added all those numbers, they would go up to infinity, because they do keep getting bigger and bigger. So there's going to be different types of problems where we add up these series, where if we get to infinity, we'll say that it diverges. But if we add them up and we get a specific number, then we're going to say it converges to that number. Okay? All right, so what's the difference between a sequence and a series? A sequence is just the numbers separated by commas. It's like a pattern. But the series is when we add them all up. Okay? And we use this sigma notation to represent that we're adding. It's a Greek letter S for sum. Okay? And so the second joke is, what is this? Remember what this is? As I think, Weston, I think last year, I told this joke in the trig class. No? You don't remember all my jokes?
I don't remember this. I do remember the infinite bar joke, but
Okay.
I don't remember this one.
Well, this is the World Series. Okay? This is the World Series. So anyway, I actually did have a student that had me for 2 years, and every once in a while he would bring out this like a composition book, and I would see him start writing in it, and I'm like, what are you doing? Because it would be at a weird time in my lecture. It wouldn't be like an important like note-taking time. All of a sudden, just sort of at random time, he would pull out this ledger and this composition book and start writing in it. And he did that for about a year and a half, because I had him all through trig pre-cal, and so for those two classes, for college algebra and trig, and then I had him in Calc 1. And it was seemed like maybe it was the end of Calc 1 or the beginning of Calc 2. He finally told me what was in this book, and he had saved all that time, and he would write down all my jokes. And I'm just like, dude, he was the worst note taker. He would never write down all the math he needed, but he would write down the jokes. So, but now I kind of wish I had him, because maybe I'd, publish them. All right. So now we're going to actually get into 10.1. So now is where you need to write stuff down. All right. So here we have a sequence, an infinite sequence. So the ... means it goes on forever. Separated by commas, it's a sequence. Now each of these are terms in the sequence. So if n is kind of keeps track of the term number. So if I say the a sub n, that just means the nth term. But a sub 3 would be the third term. So a sub 3 would be 6. Okay? All right, so here, if I said, well, what's the a sub 3? It would be 10. Okay? Now, in this case, to go from one term to the next, you don't add, but you multiply. See, in the last one, it was arithmetic, because 2, 4, 6, 8, you're adding the same thing. If you multiply by a number each time, we call that R, the common ratio, and that is a geometric sequence. Okay? Now, I know all of this is review, but it just helps with the vocabulary when I say stuff, if you kind of remember what we're talking about here. All right, and then, see, this is neither geometric nor arithmetic. But you can still write down the a sub 1 would be the square root of 1, a sub 2 would be square root of 2, then square root of 3, then the square root of 4 is 2, and then square root of 5, and so on. So this is still a sequence, and it's infinite. It goes on forever. It's just not arithmetic or geometric. Now, this little thing right here, where you have -1 raised to a power, that's called the alternator, because it has the net effect of alternating the signs. It changes the signs in the sequence. So here it'll go from positive to negative, because when the exponent here is even, then -1 to an even power will make that positive. But when the exponent is odd, then it'll be negative. And so that's how it alternates the signs. And so that's an important idea. Okay, so you can, try to look for patterns, and then this is kind of like coming up with the formula. So we've done that. Okay, so an infinite sequence of numbers is a function whose domain is the set of positive integers. So what we mean by that is that when you start counting your a sub n's, you start at 1. Okay, you don't start at 20 or something else. Okay. Now, if we were to graph, let's see. Okay, so we're still not to the first blank here. But if we were to graph the numbers in a sequence, so here's a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, they're still getting bigger and bigger. Or on an XY graph, see the numbers here are getting bigger and bigger. And so when that happens, we say that the sequence diverges. It's going to infinity, or if it goes to negative infinity. All right, now, but this one, see, here's a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. So they're getting slower, smaller and smaller. Or so, like here is a better representation. You can see the y value here is approaching 0. And so there we say that it converges to 0. So if it approaches a number, we say it converges to that number. If it doesn't, if it just goes to infinity, we say that it diverges. So like in this example, here's a sub 1 and then a sub 2 and a sub 3. So it bounces back and forth. But even so, it's the values overall are getting closer to 0. So we would say this converges to 0. Okay. So, all right, so this is our first blank. So we say a sequence and we write it as in set notation a sub n. So the sequence a sub n converges to a number L if, and remember this basically is saying that the limit approaches L. This was the delta epsilon thing. And so if no such number L exists, so if the limit doesn't exist, we say that a sub n diverges. So if a sub n converges to a number, we write the limit of the a sub n is equal to L, or this book really loves this notation. A sub n approaches L. I like the limit notation because that's what students are mostly used to. But so I would write the limit as n approaches infinity of 1 over n is 0. The book would write 1 over n approaches 0. And so, but you need to know that these notations are the same. Okay? And so if the limit exists, then it converges to the number. If the limit does not exist, then we say that it diverges. All right.
Mr. Strong.
You need more time on that?
No, I was just I was looking at my Moodle and I don't have anything for chapter 10 yet. So
the guided notes, you mean?
Yeah.
Okay,
Yeah.
so I sent them to the lab aid, but
Okay.
all I have is the first section done.
Okay.
So 10.1 is all that they should have, but they should have had that printed for you.
I'll ask her. Thank
But
you.
I don't think I posted it yet because I was going to try to finish it. So do you not have it either, Weston?
Yeah, my lab aid's not here today, I don't think.
Okay. Let's see. Let's see if I can put this up really quick because it's on the same flash drive. Okay. Okay. So it should be on the website now. Oh, crap. Oh, I just put it on the wrong one. So hold up. Okay, so sorry about that. Sometimes it's a little easier to manipulate the Moodle than others, so, but I think I got it up there. Okay. All right, so let's look at some examples here. Now, the nice thing is that when we're talking about convergence and divergence, to really limits that we've already done. So hopefully this is not going to be, this is going to be a little quick review. So basically, whenever we have infinity in the denominator, that as the denominator gets bigger and bigger, then the fraction gets smaller and smaller. So we would say this goes to 0 and it converges. So it converges to 0. Now in this one we have a constant. Well, as n gets bigger and bigger, see there's nothing to plug in here. So it doesn't matter what n does. K is still going to just go to k. So this is going to converge to k. All right. So the answer here is circle K. I'm just kidding. Actually, circle K is what caused NPC's blackout yesterday. I don't know if you knew that we lost power. It was all because of circle K. So, all right. So see if you can do practice 1A and B. And if you don't see that yet, let me go ahead and pop those up. All right. So Weston, what do you think about the first one?
Converges at 0.
Yep. All right. And how about the second one, Jada?
Converges.
Yep. So this one converges to 5. Okay. All right. Limits at infinity. If the sequence diverges to infinity, we write the limit of the function as x approaches infinity equals infinity, or a sub n, and then the little arrow goes to infinity. If the sequence diverges to negative infinity, we write the limit of the function as x approaches infinity is equal to negative infinity, or a sub n approaches negative infinity. So either way, infinity or negative infinity, the answer is diverges. All right. So now in this example, see the numbers don't really approach anything. They bounce back and forth between negative and 1, between 1 and negative 1. So this is an example of where it diverges, but it doesn't really diverge to infinity or negative infinity. But it still diverges because it doesn't approach some number. Okay? All right? So think about that one for a minute. So, Weston, what do you think about that one?
I think it diverges.
Yes. Because as x goes to infinity, the square root of x is still going to go to infinity. So that diverges to infinity. All right, now, these are some of the rules for limits of sequences. And really, these all work the way that you think that they should, okay? So, it says let a sub n and b sub n be sequences of real numbers, and let capital A and B be real numbers. The following rules hold if the limit as n approaches infinity of all the a sub n's is capital A, and the limit as n approaches infinity of the b sub n's is capital B. All right, so the sum rule. If you're adding two infinite series together, if you're adding two series together, you can just add the limits. Or you can subtract the limits. Or you can multiply the limits. Or if you have a constant times one of this series, then it's the constant times the limit. Or if you're doing the limit of their quotient, it's just the quotient of the limits. So this is kind of nice because everything works how you think it ought to work. All right, so let's do some more examples. All right, so here, as n goes to infinity, then again, this will become smaller, but it's negative. So, but it's still, so you can think of this as -1 times this limit. But this limit is going to go to 0, so 0 times -1 is still going to go to 0. Okay? So we would say this converges to 0. All right, now, there's a couple of ways that we could do this problem here. But if ever your denominator is a monomial, so it's just one term, you need to remember this little trick where you can break it up and say it's going to be n over n, which is 1, minus 1 over n. All right, now, then the limit of 1 is just 1 minus the limit of 1 over n, which is 0, So this is going to converge to 1. So this little trick as far as splitting the fraction, that's always a great one to use if you have a monomial in the denominator. All right. Now, here we have the denominator going to infinity, but a constant up here other than 1. Well, it really doesn't matter what the constant is, if it's 1 or 5 or a billion. As this gets to infinity, goes closer to infinity, it's going to swamp the numerator. And so the denominator is going to get huge, and so this is going to go to 0. So it doesn't matter what the constant is. Okay? All right. Okay, one more. Now, this one, the trick to remember in doing these limits is actually from pre-calculus. That a limit at infinity is like finding a horizontal asymptote. And you might remember what we did here is we compared the powers. So if you have a polynomial here and here, you compare the powers. If the power is bigger in the numerator, it'll go to infinity and diverge. If the power is bigger in the denominator, it goes to 0 and converges. If the powers tie, then it's the ratio of the leading terms, -7/1. So this is going to converge to -7. But this is how most books teach it, is they'll teach you to just divide by the highest power. And then see, and that's how I was taught. And see, then this constant over into the 6, that goes to 0. These cancel, so they'll go to -7. These cancel, go into 1. This goes to 0. So -7. But remember, I was able to do that in my head because when the powers tie, it's just the ratio of their coefficient. So -7/1, so -7. So this would converge to -7. Okay? All right, so go ahead and try practice 3, all 4 of those. All right, Jada, what do you have for A?
I got it converges to 0.
Converges to 0. All right, and Weston, how about B?
Converges at 1.
That's right.
2, 1.
And let's see, let's go to the next slide, I guess. All right, so Jada, how about C?
Converges to 0.
And Weston, how about D?
Converges to 5.
Yep. Okay, any questions? Any of those you want me to explain in more detail? Okay. All right, so next we have the sandwich theorem for sequences. So you might remember when we did the sandwich theorem, that's when we did the Arabian Nights and Shahrazad's tale and the 2 platters in the desert that they were trying to find the black grain of rice. But the idea is that if a function lives between two functions, and these two functions come together at a limit at a certain value, then the function in between must be at that same limit. All right, so how that works with sequences is if you have three sequences, and let's say b sub n is between the other two, then if the limit of a sub n and the limit of c sub n is L, then the limit of the b sub n's is also L. So it works the same way that the sandwich theorem did for us back when we originally studied limits. Okay? So then let's say we know that cosine is always between -1 and 1. All right, we know that. All right? And let's say we divided them by n. So now we wanted to know what's the limit of cosine n over n. Well, we know as n approaches infinity, a constant over infinity is going to go to 0. So this goes to 0. So since this lives between these two, its limit is also going to be 0. Okay? So even something that maybe is not real obvious, you can use the sandwich theorem. All right, so see if you can figure out practice 4. Oh, the key, I think I skipped the key theorem here. Let's go back. Okay, so the key theorem is this, that the limit as x approaches infinity of any constant over x is going to be 0. All right, so what's this going to approach as n approaches infinity?
0.
0. See, it's kind of hard to reason this one out, but again, this goes 0, 1 over